Hi. Look, thus far, I've been using word derivative to describe, of course, a limit with delta x approaching 0 out of the difference quotient. So, our measure of rate of change of the function at one given point. And it was of course correct, but when we talk about derivatives, what we mean by this is usually first derivative. But look, first derivative is not the only type of derivative we can calculate. And this is what I wanted to tell you right now. So look, if we have a function y equals f of x, remember we will calling it primitive function. Now, look, what I can do over here is, of course, to calculate derivative of this function, dy dx, right? Which is the same as f prime of x. And this we call derivative function. But look, I differentiated this function just once. So the precise terminology for this would be calling it the first derivative. Okay, but now look, I can go further with this. What do I mean by that? Look, what now? If I want to differentiate the function for the second time. So look, this is still our primitive function. This is the derivative we've already calculated. And look what I'm doing right now. I'm taking a derivative of the derivative. How would it look? Look, this would look like this. I'm taking the derivative. Remember, this is a command. Take the derivative of whatever is up front. And sometimes we put here y, like here, because this is derivative of this function. But now I'm calculating the derivative of a derivative. So what is going to happen now? Look, the good thing is that we can combine what we've got over here to make this a little bit more pleasant looking. And let's start with upstairs. Look, what is repeating here? D. So why not write it as d squared? And over here, we've got dx times dx, which would give us dx squared, right? But the convention is to simply write it, in this case, as dx squared, but remembering, of course, that here we've got x dx twice. Okay, and look, this is how would we write the derivative of the derivative in the Leibniz notation. We can, of course, do the same thing in Lagrange notation, and we would have this, another prime, right? So we're going to call this the second derivative. Oh, can I get third derivative? Of course, why not? Now I would have to just take derivative of the second derivative. So I would have d3 y dx3, or in Lagrange notation, 3 primes. Okay, so we've got third derivative. Look, how many derivatives can we actually calculate? We can, look, even 0, which has derivative 0, which has derivative 0, which has derivative 0, we can take this derivative as many times as we want. and usually as many times as needed. The thing is, there are some functions that simply go through some changes when you apply derivatives. Some would stay the same, like e to the power of x or constant function. And the case that we're not going to discuss right now, but we will in the future, are derivatives of trigonometric functions, which actually turn from sine you get cosine, cosine you get negative sine, and then you get from negative sine, of course, you're going to get negative cosine. From negative cosine, you're going to get negative sine, so sine, and this pattern is going to repeat indefinitely. But we're going to go back to it a little bit later. For now, let's just think, how could we write down nth derivative? Okay, so our nth derivative would be the n, of course, here, right? Because we have 3, like here, 1, 2, 3, then y, d, x, n. Which, of course, we can also write in Lagrange notation as f n x. And this is nth derivative. Okay, look, as you see, this is very easy thing to do. So let's just illustrate it with one example, and I think this should be enough for us. Okay, so look, we've got that y is our function f of x. So this is 4 times x to the power of 4 minus x to the power of 3 plus 17x squared plus 3x plus 1. Okay, now let's calculate derivatives of this polynomial function as long as it makes sense to do that. Okay, so first, I of course calculate first derivative. So I can write it either as dy dx or as f prime of x. And I'm getting that this is 16x to the power of 3 minus x 3x squared plus 34x plus 3, right? 1 is gone in differentiation. Then we can calculate second derivative. So d squared y dx squared equals to f piece x. And now we've got this is 48x squared minus 6x plus 34. Okay, now we can calculate the third derivative. Here we will have 96x minus 6. Then we can calculate fourth derivative. And look, here nothing new is happening. But over here, look, instead of writing primes, we're going to simply put 4 in parentheses on the top. It needs to be in parentheses, so we are, for example, not going to confuse it with taking a function to some specific power. Okay, and now we've got that this is 96. Okay, now we can go, of course, further. And if I'm going to calculate derivative, fifth derivative, so, okay, I'm going to be just using Lagrange notation because it's easier. And look, usually when we calculate derivatives of just one function, this is the, a function of just one variable, is, this is the way to go. So now I have, look, the fifth derivative, in this case, it's going to be 0. But look, this means that it is the same as the sixth derivative, as the seventh derivative, and until nth derivative. Of course, remember, this is not always the case. Sometimes, doesn't matter how many times we differentiate the function, we will never reach 0. That is the example I've been telling you with the trigonometric functions that actually change their derivatives every 4 differentiations, and they go back to the function that we actually started differentiating. But look, for now, for illustrative purposes, we will be mostly dealing with polynomial functions because they have a very nice maximum and minimum that we can find using calculus. So over here you see actually we will be going to 0 at some point. Okay, so this is it about higher order derivatives. The interpretation of these derivatives is something that we're going to start discussing in very much detail since another video. But of course, look, there is something called nth derivative test that we're going to discuss in the future, not now, but for the remainder of this class, we will be interested in those two. Because those two derivatives are giving us enough to draw any continuous function we want. Okay, so thank you for your attention and see you in the next video.